Professor of exoplanetology and fellow at the University of Birmingham. Professor Amaury Triaud is known for discovering more than 100 planets, an expert on the formation of planets and the physical processes that cause them. Last year, he was a core part of the expedition to set up a new mount for ASTEP in Antarctica, a telescope specially designed to detect other planets in our galaxy. And he is here to tell us about his journey and the discoveries that were made during it. Professor Triaud, you have the floor.
Yeah. Thanks, man. So indeed, today the idea is to give you an idea, a description of the work that happened in Antarctica. I will start with a bit of context about exoplanets, various methods that we use, and I hope that towards the end, as I show you pictures and work that happened there and results that we're having with the telescope, you understand why we are going to Antarctica. So the title here, New Worlds, refer to exoplanets, and Antarctica to another world, because it really was another world. Although I worked a lot with my colleagues that go to Antarctica, they described to me a lot that place. It was different being there, and it really felt like stepping in a different planet altogether. Strangely enough, I started getting involved in this work in Antarctica when I was a fellow here at the IOA in Cambridge, where the PI of ASTEP was searching for new collaborators, and I joined the University of Birmingham soon afterwards, and then became, a full participant in that endeavor. So, what is ASTEP? So ASTEP is a 40-centimeter diameter mirror telescope. So 40 meters, it's fairly modest in terms of size. It has a simultaneous dual band camera. So we observe in a blue and a red band simultaneously, and you'll see, I hope later, why we're doing this. And ASTEP is located at Concordia Station, which is a Franco-Italian station, research station inside Antarctica on the Antarctic plateau at Dome C. The station is 1,200 kilometers from the sea and 3,200 meters in altitude. But in the winter, because of temperatures going down to minus 80 degrees, because of the slightly increased gravity at the poles, you end up with an atmospheric pressure which is similar to being one of the highest sites on Earth. And that is one of the main reasons we're going there, because the long austral winter night and the the lack of atmosphere on top of our telescope make our observations rather extraordinary. I'll keep on describing a little bit of the instruments that I use so that you it's the jargon in a way, so that during the talk you understand what I'm talking about. So ASTEP is a collaboration between the Observatoire de la Côte d'Azur in Nice in France, the University of Birmingham, and the European Space Agency. And you see here the various scientists that are involved here. And I would say a special mention to Vincent Deloupy here, who has been a wintering over person for the past year. So it's a 15-month mission for him. It was out there throughout the winter. So Concordia is so isolated that they can't get out after the 31st of January. That's it. If there's a problem, they have to deal with it on their own. The nearest station to Concordia is Vostok Station, but it's not inhabited in winter, and it's 600 kilometers away through the ice. And sometimes the nearest people are just simply in space where they are. So it's quite of a special location. Among those people, Karim as well is very well known in Antarctica. Karim has been going there since before Concordia Station existed. So before the buildings were put on the ice, he was there already testing the site and making sure that the conditions were good. He has 22 years of Antarctic experience. And without him, I don't know what we would be doing. He's the chief engineer of the telescope. Another set of telescopes that I use are in Chile, in the Atacama Desert. So this is Speculos. Those are 1 meter diameter telescopes. So again, modest size, quite a bit bigger. Why I'm bringing this up is because they're somewhat related, notably because the telescopes here operated with direct drives. So direct drives are electromagnetic motors. There is no contact. We use magnets to move the various axes, the two axes that the telescope needs to point. And it turned out that this was a very, so the mount of the telescope is actually a robot from an assembly line for car manufacture. You know, those robots that screw things everywhere. You can put a telescope on that, and that works extremely well. So my experience with this telescope is that you buy them, and then at the moment, so it's a collaboration again between several people, but the one I'm responsible for costs us between £5,000 and £10,000 per year to run, which is so small. And that includes electricity, internet, engineers for maintenance, cleaning the mirror, everything. So it's really, really cheap to run. And the old ASTEP telescope used a crank to move the mount, and because of 10 years of Antarctic service, metal, you know, moves when you have changes in temperature. Sometimes we have changes in temperature of 50 degrees in one day. It's actually incredible. So imagine the stress on that sort of equipment. And so the old mount of ASTEP, well, was wobbly in the end. And so my participation was to bring, find the funding to bring a direct drive to Antarctica, and it's been operating now since, so we installed it last year in November, December, and it's been operating since March and has been operating really, really well since. So Speculoos, those telescopes will come back in a minute. They specialize in the observation of very small stars. And then the other instruments that I might mention at some point, and just placing them here, are two spectrographs, one in Provence. I was actually just there. I came back from Provence on Friday, where I was observing. This is the telescope that found the first exoplanet, incidentally, and Espresso and HARPS in Chile. Right. Before going further into exoplanets, I also wanted to show you a little bit what Birmingham was. So this is a view from the Department of Physics and Astronomy at the University of Birmingham. So we are in a very, very lovely location. We're happy about this. This is what it looks like as a city. I know Birmingham has a strange reputation in the UK, but ever since I've been there, I've been absolutely happy with my situation. So I try to recruit. And since this is the Students' Astronomical Society, I thought, you know, I'd put my little bit of advertisement to attract you to the second city of the UK. This is the group that I lead. So the original leader of the group was Yvonne Ellsworth. She won the gold medal of the Royal Astronomical Society a couple of years ago. She's now almost fully retired. Bill Chaplin also then was head of group, and now he's a head of department. And so I took over from Bill. And this is the lineup that we have in terms of permanent academic. And we also have 11 postdocs, 8 PhD students at the moment. And among the students, one of them is a Bell Burnell Fellow, and the other finished one of the postdocs, actually, who was a student, won the Royal Astronomical Society PhD prize. So just to say that our department is small, it's a small group, but very active, and we're very, very friendly as well. And in addition, the School of Physics and Astronomy, I think, to a surprise of many in the UK, it turns out that it's the place that does the most 4-star rated paper in the UK in physics and astronomy. So consider us for your PhD or further study. Right, without much further ado, let's go into exoplanets. So I'll start quite easy, and then I'll narrow down on methods and what brings me to Antarctica. So an exoplanet, as far as I'm concerned, is a planet orbiting another star than the sun for the rest of this talk. I know this definition is not accurate in that we know more and more that there are planets without stars. Yeah, those don't orbit. I don't think they lose the definition of planet, but for the purpose of this talk, that's what an exoplanet would be. And why do we study exoplanets? So what drives the field mainly is to find evidence that biology has emerged elsewhere in the cosmos. And that is certainly something that I'm absolutely fascinated to do. And you'll see the talk will go into that direction, into identifying the most planets we can to understand temperate climates, to understand habitability, and eventually identify biology. Another bit that interests me a lot is that middle part here. I believe that as astronomers, we are sort of the custodians of thousands of years of oral tradition. We've always, as humans, tried to make sense of the world and created mythologies and all sorts of stuff. And as astronomers, we continue that tale and we tell it to the public. And so finding out what is there, describing it, telling people what is nature, what is the universe, is a human entered the waiting room. Hello, I come in peace. All right. Yeah, so I think that's an important part, I think, of our role as astronomers is telling the public about this and completing, in effect, the tale of the creation and understanding our position within the rest of the cosmos. Finally, we want to understand the physics of planet formation. So by collecting data on multiple types of exoplanets in multiple types of settings, different stars, different ages, etc., we want to tease out what physics happens during planet formation. I'll show you that part in an instant as to why it's an interesting problem, but also a difficult problem to tackle. And beyond that, I think what exoplanets allow us to do is to explore new climates. It could eventually lead us to measure the frequency of climatic tipping points. So how often, for instance, do you go through a runaway greenhouse effect? How often do you go through a snowball phase for the Earth, like we've detected on Earth? So far, Earth is the only place where we have traces of active plate tectonics. So we could actually also investigate that. And there's all sorts of other sub-questions which are of, I think, particularly high interest to me and many others. So now on to a little history of exoplanet detection to give more context. So here what you have is the orbital period of your planet in years. So Earth is here, and here you have mass in units of Jupiter. So Jupiter is there, Saturn, Uranus, Neptune. And that's Earth and Venus. Mercury is below here, Mars is below over there. And in 1990, that was all of what we knew about planets in the universe. And most of the teams were understanding planet formation because of 3 lines here. So if you're far away from your star, at some point, water will go from vapor to ice. And so there will be a water ice line. And at some point, CO2 will go from vapor to ice, and there'll be a CO2 ice line and then a CO ice line. And why this is relevant is that while here you would only have dust, here you have dust and ice, and here you have dust, ice, and CO2 ice. And so you end up with more building blocks, effectively, the further out you go into the system. And so it looked like it was normal that the big planets would be further out, and normal that the smaller planets would be inside of it. And 30 years of research have shown that really we didn't understand that. Big stuff can exist quite close to the star. And I think that's why, you know, like the exoplanets are really crucial to understand the physical processes behind planet formation, because you can see how much of a mess this is, right? Planets seem to exist almost everywhere. Sure, they seem to congregate in subpopulations, but making sense of that diversity is difficult. So the main populations are the hot Jupiters. They exist around 1 star in 200 roughly. So the fact that we have so many is just because they're easy to detect. Here we have warm and cold Jupiters, so things closer to the idea that we have of our own Jupiter. And you see this big population there of super Earth and sub-Neptunes. So although here they don't look like there are too many, actually half of stars that you see in the night sky will have a planet more massive than the Earth within Mercury's orbit, half of the stars. And this is by far the most common type of planet in the universe that we know of, at least around single sun-like stars. And well, we're jealous. Why don't we have one? And effectively, we're trying to understand what are these planets? Are they small versions of Neptune? Are they large versions of the Earth? Are they totally different yet? How do they form? Are there several methods for forming them, etc., etc.? Now, this plot here is only for a single sun-like star. So there is another axis here of diversity, which is the type of star you're about. And if you do a census of the solar neighborhood, you find, so here is a histogram, so you count objects within 10 parsecs. Here you rank them in terms of their mass. Sun-like stars are here, 1 plus or minus 10%. And you can see that the majority of stars are tiny, right? 3/4 of stars are, you know, like half of stars are less than 1/4 of the mass of the sun. And so it means like here around sun-like stars, you have only 15%, 15% of stars, but half of those are already in pairs, in binary stars, and usually they're typically excluded from planet detection program. So in fact, the plot that you were seeing here, that's around only 7% of the galactic content of our galaxy. So I made it sort of my role to explore the 93%. I thought that it would be very interesting because half of stars in our galaxy are binary stars. I'm going to look for planets around them because it's a massive number and we don't understand that. Half of stars have masses less than 1/4 of the sun's, and that's where I'm going to look for planet because that's maybe where most of the planets actually lie. And then it turns out that 50% of single sun-like stars also have these super Earth things that we don't have, and that is also a massive number. And therefore, I'm going to look at the majority or close to the majority of systems rather than single out, you know, solar system-like or smaller proportions of stars. If you retain any number, I think, from this talk, I think that's the one to retain, because I think we always think of the solar system as being representative of what is out there, when in fact it isn't representative, in the same way that, you know, it's hard, I don't know, it doesn't mean that the solar system is rare, but certainly it's not a copy that you see everywhere. And that is something, you know, I was telling you at the beginning that it's important to relate to the public about what is nature, and that is certainly one of those facts, I think, to relay out. So how do we detect exoplanets? So the main method that we're going to talk about today is the transit method, and I'm going to briefly outline how it works and why it's an important method. And it's the one that ASTEP in Antarctica is using. Transit method is conceptually fairly simple. So this is footage of the sun in 2012. And you see Venus passes in front of the sun. While Venus is in front of the sun was a little dimmer. And that is what we're looking for. So in reality, it looks like that. So we have a star and we have our planet here. And if we have something like the size of Jupiter transiting the sun, we will have a drop in brightness of about 1%. And this is not difficult to detect. So we can detect it with fairly small telescope, so long as they have a very good detector and a very stable detector. In practice, the way we do it is that we take an image of the night sky and we're going to compare the brightness of, say, this star against the brightness of all the other stars around. And every dot here is one picture. And then on some of the pictures, this star is a wee bit fainter, effectively. So all of what we do comes from this light curve, okay? So that's all of the information we have. We don't see the planet. We only see the effect the planet has on the star. And we don't see much, right? It's a time varying signal, and that's pretty much when we have information about the planet. There are other methods that give us information at other parts of the orbit, but as far as we're concerned for transits, that's the only time we have signal. We can modulate this signal in various ways. One of them is if you have several planets. So this is a light curve from the Very Large Telescope on the system called TRAPPIST-1 I'm going to introduce a bit later, where you can see here on that night, 2 planets came in transit, a third planet came in transit, 1 came out, second came out, third came out. You can see here a depiction of the system here. And you see like all those were single images taken by the VLT. And I will show you several light curves, as why I want to make sure that you understand, you know, what those transit light curves are like, so that later in the talk you can recognize them just without me saying much more. We want to study and find planets in transit because while the planet is in transit, some of the starlight will shine through the atmosphere, and thus we can learn about the atmospheric composition of the planet. So I'm going to give you ways on how we can study the planet's atmosphere by using the moon. So what can we deduce about the Earth's atmosphere by looking at the moon? So during a lunar eclipse, we have this sort of configuration, right? We have the sun, we have the Earth, and we have the moon. And the only light that reaches the moon is sunlight that went through the atmosphere of the Earth. So we have sunrise here, sunset here. And the reason why the moon is red is because it's illuminated by all the sunrises and sunsets of the Earth, which is, I think, a nice poetic way of looking at a lunar eclipse. And if we place a spectrograph towards the moon on a night, we can get the following spectrum. So you see here flux, here wavelength, so bluer, redder. You can see it brighter in the red. Okay, you don't need a spectrograph to see that on the picture, but it's nice to see it gets confirmed. And you see various things, right? You detect oxygen, you detect water vapor, you detect ozone, you even detect some pollutants here, showing that we can be very sensitive to many species. I say sometimes, with this data, we're trying to find whether, there is life elsewhere. We can even detect, human stupidity on this kind of measurements. So they're quite sensitive as it is. Now, imagine yourself in the middle of the circle here, looking back at Earth, and try to think what it would look like to look at Earth during a lunar eclipse. Can you picture something in your mind? Yeah. So there's only 3 humans who have seen that, and they were in Apollo 12. And when they deorbited the moon, one of them had the presence of mind to grab the video camera and take a 12-second clip of this. So this is the Earth. You can see the sun is very red. That's the sunrise-sunset effect, right? Our atmosphere scattering blue light. And this is the signal that we want to find on an exoplanet, okay? This is what contains effectively all of the atmospheric information, the chemistry of the planet, blah, blah, blah. Let's go back to this one. Who in the audience can notice the atmosphere of Venus on this footage? Right, difficult, huh? Yeah, it's rather tough. Well, Venus has a big atmosphere. It's the nearest planet to us, the only one for which we can see time-resolved images. And where is the atmosphere? Very difficult. So how do we do it? Well, in exoplanets, what we do is use a trick. So we call that method transmission spectroscopy. And if biology or biological gases are detected in the atmosphere of an exoplanet in the next few years, this will likely be the method that will do that. So it's a word that is worth remembering. So imagine we have an atmosphere-less planet here. It passes in transit, and we measure the size. Okay, you see light rays are being stopped. We measure the size of the planet. That's what a transit does. Now, if we place an atmosphere around the planet, how is that transit depth modulated? Right. So the bluer wavelengths here get interrupted by the atmosphere of the Earth here. And so we will measure an apparent size of the planet, which is the radius of the planet plus the opaque part of the atmosphere in that particular wavelength. And in a redder wavelength, just like what happens during a lunar eclipse, part of the atmosphere is transparent in those wavelengths. And so we will measure a slightly different size in those radar wavelengths. And so this changes of apparent size of the planet as a function of wavelength is how we do transmission spectroscopy and how we extract an atmospheric signal. And here it is in practice. So what you have here is wavelength. Here you have the relative size of the planet. And you can see that here at 1.4 micron on that particular planet, the planet is a wee bit larger, and it corresponds to the absorption band of water. And so there's water vapor in the atmosphere of that particular planet. So the signal I think that we need to bear in mind is that transmission spectroscopy only happens here, right, at the terminator between day and night. There is another way to study an atmosphere, which also sort of implies that the planet transits, except that here, instead of the planet passing in front of the star, we're looking for the planet to go behind the star. So, and the sort of data that we have look like a transit, except here it is an eclipse of the planet by the star. And so what you see is the star plus planet flux. Here, the star flux as the planet is behind and we don't see it anymore, and star plus planet flux again. And so the deficit here must have been emitted by the planet. And so we can place that in a diagram as well. And you see here the brightness of the planet as a function of wavelength. is the same planet, and you see the same sort of absorption here in the emergent flux caused by water absorption in that planet. And so on two sides of the orbit here, we can measure water vapor. And so those are the two methods. This is my favorite method, actually. Emission spectroscopy is harder to do, but I think we actually learn more with it. And also we get the full day side of the planet. So we get the atmosphere more of an average atmosphere than on the other method where we get a very special area, the day to night terminator. Now, this emission spectroscopy is similar to another thing that happens on the moon, which is the Earth shine. So when you look at the moon, you see that sometimes it has a very, very tiny crescent, right? And the dark side of the moon is actually not totally dark. And that's because sunlight reflects off the day side of the Earth, bounces off the night side of the moon, and bounces towards the night side where you are with your telescope. And so effectively, this Earth shine here is really a picture of the day side of the Earth, seen from the night side of the Earth. Again, a weird way, to appreciate that. And if you place a spectrograph there, you can see a lot more structure, which is why I think this reflection and emission spectra are more interesting. You see, again, flux here as a function of wavelength. And here it's bright in the blue, faint in the red. And so it means that, it's sort of blue here. This is the color of the sky. So that's the blue sky, the Rayleigh scattering that's happening. You see water, oxygen, CO2, methane, ozone again. And the fact that it goes a little bit up here is what we call the red ramp. That's vegetation. So vegetation reflects and emits in a near infrared. And you can actually see that on the spectrum that the Earth reflects on the moon. And so there's a hope eventually that's the sort of stuff that we can do on exoplanet as well. Harder measurement to make, but more interesting, a lot more information. There are two other things that one can do. So for atmosphere, so this one doesn't absolutely require planet in transit, but if it does, it's actually quite convenient. So you can see that as the planet orbits its star, it will wax and wane like our moon, right? So the fact that you have a bigger view of the day side of the planet here than here means that the integrated light that we will collect will change as a function of time, and that we call a phase curve. The phase curve looks like this, and it's important because we have attempted this kind of observation from Antarctica. So what you see here is, again, the flux from the star. And you see here the transit, so that's the planet passing in front of the star. And you can see that it goes a wee bit up, and then that's the planet going behind the star. The dashed line here is the flux, the nominal flux from the star, and then it reappears. And here you have a zoom of this little part over there. So on the bottom part here, you can see better the phase curve. So what this is telling us, so this was taken in infrared. What this is telling you here is that this is the day side temperature. And here, the flux that happens just around transit is, you see the night side here of the planet. So you can measure the difference in temperature between the day and the night of your exoplanet with this kind of measurements. Why I like that particularly, because as, I'm an astronomer, but I'm also a physicist, and this kind of measurement gives us the energy budget of the planet. How much is coming in, how much is coming out? And therefore, it gives us an idea of what goes on in the atmosphere. Rather than butterfly collecting, molecules and things that we see in atmospheres, this actually tells us, like the sort of physics that could happen there. And a final aspect that one can do when you have a transiting planet is create a topographic map of your planet. So as the planet goes behind the star, it will go through what we call ingress, and the stellar surface will probably cut slices of the planet as a function of time. And as the planet goes out, it will also slice it the other way. And so how fast flux is dropping when the planet goes behind the star, and how fast flux is recovering as the planet exits the star, gives you two maps, which if you combine, give you the equivalent of a latitude and a longitude, and you can create a map. And this is the sort of stuff that has been done on, at the moment, only one exoplanet. The James Webb Space Telescope currently flying is going to do that on more planets than that. And this sort of method allows us to build this sort of thermal maps, but also eventually chemical maps of where certain chemistry happens in an atmosphere. And if we manage to do that, so this is in emission, if we manage to do that in the reflected part of the spectrum, then in the atmosphere is clear, then we could get a topographic map, like see big areas like Sahara is being bright, Antarctica is bright, the ocean's dark, sort of thing. So what do we learn about exoplanets in transit? And so through all of this, we learn under which conditions atmospheres can exist, because we still don't totally understand how an atmosphere persists on the planet. We can measure the chemical abundance of an atmosphere, elemental and molecular. We can also study the diversity of climatic conditions. So imagine if you look at rocky planets in the solar system, we have Venus, we have Earth, and we have Titan, or the three main types of atmosphere. Mars has a sort of a small tenuous atmosphere, but with the three main ones, you have three planets with three very different type of atmospheres. Now, if we did that on 20 rocky planets, what would we find? Would we find 20 different type of atmospheres, or would we find 3 types? We don't know, but that's the sort of thing that interests me. We can also measure the fraction of cloud cover from some of these measurements, and measure how temperature changes with vertical atmospheric pressure in the atmosphere. Eventually, so this is what has sort of been done on a number, typically on gas giant at the moment, but we're moving to smaller and smaller planet with these kind of measurements. But eventually what we might want to do is to measure surface conditions, to monitor planets across time, to do weather monitoring, and that's where Antarctica might have a role, because we can stay there for very long. Biosignatures, so gases created by the presence of biology. I will talk to you about how to infer the presence of liquid water in an instant. Already, actually, I should update my slide. We can measure isotopic ratios in exoplanet atmosphere. So for instance, oxygen 16 to 18 has been measured. So it means that we can start comparing systems to systems, comparing with the isotopic ratios that happen in the solar system, see if we're weird or if we're normal. People have started measuring wind speeds in atmospheres, which is rather extraordinary. And right now we have a series of proposals for the James Webb Space Telescope for atmosphereless planet to start measuring the average mineralogy on the day side of exoplanets to see if the surface is more like basalt or olivine or any other sort of thing that we put on. And the reason I put that on is because I think when the first exoplanets were identified 30 years ago, I don't think people had realized then that we would be in that situation 30 years hence of being able to measure so much. And all of that tells me that effectively the exoplanetology, which is a field of astronomy, is more and more turning into a geophysical sort of science, where we will need to understand processes like what happened on the Earth to make sense of all of that. And actually, I think that's what's also exciting in the field, to answer big questions like, how do plate tectonics start, for instance, and take a sample of planets and try to investigate that. Right. So now I'm going to bring up the concept of habitable zone just so I can use it a bit later. The habitable zone is a concept that I don't particularly like, but the public really, really connects with. The idea is that if you take a planet like the Earth, that if you move it closer to the sun or further away from the sun, there is a point where at some point the planet becomes not habitable, meaning that so habitable, by the way, means not that you can go and pitch a tent and live forever on that planet. It really means that liquid water can persist for billions of years. And if you move that planet a little closer, then the atmosphere gets, the planet gets too hot, water is lost, and that's what happened on Venus. If you move it too far, it can freeze over, and that's maybe what happened to Mars. So you have this sort of not too hot, not too cold sort of zone. And this is related to the star you're around. So if you go to small stars, the habitable zone comes closer to the star. And that's really convenient because you can go a lot quicker. And why the Speculoos telescopes in Chile are observing those small stars, because then we can go real quick. Now, the reason I don't like the habitable zone is because it's really based on our idea of the solar system. And I think everything that we've learned about exoplanets is the solar system is not representative. So I think we need to be a little more imaginative there. And also, I think people have become a bit obsessed with finding planet within the habitable zone in the field, when I think actually this is a theoretical construct at the moment. It has nothing empirical to it, and that we should first try to make it empirical and then measure where it is so that we can confront the models to actual data. And yeah, I'll go a bit in that, and that's another reason why Antarctica will end up being useful. So one archetypical system in the habitable zone is TRAPPIST-1. The first talk I gave to the Student Society was about this, just about 2017 when the paper came out, where we discovered 7 planets around this star, 10% the mass of the sun, 3 of them within the habitable zone. And at the moment, all of them are being observed by the James Webb Space Telescope in order to look for signs of atmosphere. It looks like the innermost 2 planets don't have an atmosphere, and so we're slowly going to outer and outer planets to find out whether some might. Now, because of getting caught in the frenzy of TRAPPIST-1 and all this, I started with some of my colleagues actually from the TRAPPIST and Speculoos team to change a bit the debate from finding planets that are in the habitable zone to use a different word. And the word that we use in the team is to look for temperate planets. And by temperate, we mean a planet that has between 4 times and a quarter of the stellar flux received from the Earth. And the reason for that is because the atmosphere can modulate a lot whether the surface conditions are actually habitable, for one thing. Certain planets might be tidally locked with a permanent day and a permanent night. So even a planet that is too hot on the day side might not be on the night side, for instance. And because we want to be able to study the transition from planets that do have water to not have liquid water anymore, empirically. And weirdly, all of the science that I've been doing lately somehow seem to converge on finding temperate planets. And so with Speculoos, we're looking for temperate sub-Neptunes and Earth orbiting the lowest mass star in our galaxy. I'm going to describe to you a little bit about finding circumbinary planets, which use HARPS and SOPHIE, which I showed you pictures of, and ASTEP in Antarctica. And that was actually the main draw to me to find to Antarctica, was to allow the study of circumbinary exoplanets. It turns out that with ASTEP, we've done a very good job at measuring, detecting, confirming repeatedly temperate Jupiters and Neptunes transiting sun-like stars. And we really specialize in that, and I'll show you results from that. And lately, we've also done temperate gas giants using M dwarfs on Speculoos. So just to give you an idea, yeah, so Speculoos is this telescope. So we're doing really well. So here is stellar mass, and you see all sorts of planets here, and here is incident flux. So planets are hot and clusters, star here and colder here, and you see the sort of temperate zone here that I was describing. And you see here the known planets. And all of the purple dots here are planets that have been either detected or confirmed by the Speculoos array. And we're doing about half of the temperate rocky worlds at the moment. And I'm really proud of that. So we are hopefully building a sample large enough that eventually we'll be able to study the very notion of habitability and bring a bit of empiricism to it. Which brings me to this paper that appeared 3 days after I came back from Antarctica. There was a problem with the editors. They didn't understand that I was about to leave and not be in email contact for 2 months. And they read my out of office message. And after the 4th time, they say, "Oh, you're really there. And you really don't have access to email?" Yeah, I really don't. Anyway, eventually got published, so it's good. So the reason why I'm doing this sort of little parenthesis here is because I want to advertise the concept. So we have, in a body of work of astronomy, we have a lot of literature on biosignatures, how to define, how to detect, what to do, how to combine gas signatures that could have been the product of biology. And a lot of research is going on into that. But in terms of figuring out whether a planet has actual liquid water on the surface. There is very, very little. And it struck me that there is something in geophysics that's so obvious to geophysicists, they don't even think about it, that somehow was not present in astronomical literature. And that paper is effectively a translation of geophysics in astronomy language. That Earth, if you look at the solar system, Venus has 95% of its atmosphere is made of CO2. Mars is 90% made of CO2 as well, and the Earth has almost no CO2. And the reason it doesn't is because most of it has been absorbed by the ocean and then progressively has been sedimented and sequestered into the planetary interior. And so water is actually the main driver for removing carbon dioxide from our atmosphere, and it has done so since the oceans have condensed on the surface. Biology at the moment is responsible for about 20% of the carbon sequestration. The rest is the ocean. And something very few people know is that the oceans on Earth contain 2 bars of CO2. So imagine if you released all of that carbon dioxide from the atmosphere, our atmosphere would triple in pressure, right? It's massive. And so the main idea is very simple, that if you find a planet that has, little CO2, in a system where there are other planets with a lot of CO2, then you have to ask yourself the question, where is that carbon gone? And the only way we can think of at the moment that we know of on how to remove that much carbon is water. There's no other process. And weirdly, actually, that paper, like when we wrote that paper, we went through a lot of industrial papers because there's a lot of work trying to remove CO2 from our atmosphere to solve our climate crisis. And it's really difficult, but most processes involve water, and most processes actually involve superheated water, weirdly. But they're very inefficient, and that's actually a problem that we have on our hand. So with that sort of stuff, the advantage of CO2 is that even though you might have only a little bit of CO2 in your atmosphere, it makes a very prominent absorption feature in transmission spectroscopy. And we can detect orders of magnitude variation in the shape of that line that would allow us to say whether your planet has 90%, 9%, 0.9% CO2 content. And so you need a multiplanetary system because you always need at least one planet as a calibration for that. But even if you had a planet with 50% CO2 next to one with 95%, you'd have to wonder where is that carbon gone. Another way to look at it is this little plot here, which is from the paper, which is the CO2 here in Venus's atmosphere. There's about the same amount of CO2 in the crust of the Earth. So all of that CO2 used to be in atmosphere, it's just has been moved down. And so I think that finally we found what we referred to in the paper as a terrible word, the HAB signature. Now we call it the aqua signature. We found finally an empirical way of measuring where the habitable zone is by actually measuring the active presence of liquid water on the surface or infrared. So I invite you to read that paper. But now that we have that, it means that now we need planets and in transit so that we can then measure whether or not they have CO2 and Antarctica. So it took a while to get there, but now we're in Antarctica. So I'll show you a little bit how I got there and then why we're going there and what we're doing there. So the trip is quite long. I left home on the 5th of November and came back on Christmas Eve. I was very, very, very lucky. I took the last train from Paris back to London. So the trip involved the plane from France, stopover in Dubai. Then sadly, we got rerouted to Bangalore because the baby was sick, and then carried on to Sydney. Then from Sydney, we went to Christchurch. And then we waited a wee bit and then took a military transport plane to Mario Zucchelli, which is an Italian station in this part of Antarctica. And then we took a plane called the Basler. It's actually, I'll show you a picture of it. It's the fuselage of a DC-3. It was built in World War II. And got to Concordia, which is here on the Antarctic plateau. Then I stayed for 3.5 weeks and then took the same plane back but to instead Dumont d'Urville, and that's a French base, and then took a French Navy boat to Tasmania, and then plane all the way back home. It took a long time. So the whole trip all the way to Christchurch took, you see, something like 48 hours. But like when I got to Concordia, you see that there was 2 weeks of travel before I set foot in Concordia. And on the way back, roughly the same. The crossing here took 6 days by boat. By plane, this is 8 hours, and this was 4 hours, I believe. But that plane is slow. This was what waited for me when we landed. That's the plane we took. And it was the softest landing I've ever had. As you can see on this plane, there are not many windows. I did not know we were landing. I did not know where we were. And at some point I heard the engine shut off. I was like, oh, but no, we had arrived. And then the trap door at the back opened, and then immediately you could see, so this is the frozen sea. It was absolutely remarkable. We stayed a bit in that station, so it's Mario Zucchelli. Antarctica is a place which has where the logistics is pretty intense, and there is a certain order to things, because between Dumont d'Urville here, the French coastal base, and Concordia, there is a logistical train that goes. It's not a train really, a caravan. It's a caravan on ice, and they can only make 3 crossings per year. And so the people who drive the caravan have priority over everybody else, because obviously then they need to go to get there, and then they need to drive for 10 days before they reach the station. So, and unfortunately, there had been this year or last year really now, there had been bad weather around Cape Horn. So the planes, this plane specifically, the one that took us inland, could not go from the south tip of America to Antarctica, and so they were blocked on the American continent, and so it delayed everybody, and so everybody had to wait in various places. Eventually, we took that plane. Antarctica is a weird place. So next to me was this weird thing, which oddly enough, I recognized by reading the name. It's called a hyperfine, and this is an MRI scanner. It's the smallest MRI scanner that exists, and it turns out that one of my friends invented this thing when I was a postdoc at MIT. And I was the first brain in the prototype, and we were bringing the finished product to Antarctica to study mountain sickness and stuff. And I became the first brain to be scanned in Antarctica. So I was like, yeah. But like Antarctica is really like a sort of summer camp for scientists. There's so much going on. And so it was just weird to be traveling with it. That's what the base looks like. So you see on the right-hand side, you have the 2 towers. There is what we call the quiet tower, this one where the bedrooms are, and the noisy tower where we have the living room, the dining hall, and various things. I'm going to show you a layout of the station in a minute. What you see here are workshops. This 3 containers by 1, 2, 3, 4, 5, 6. This is the oil petrol reserve for the winter. So your carbon footprint is very tangible when you're there, and you can actually see it. In this kind of containers here, you have various things. You have the power plant, and you can see the little smoke here is the power plant actually producing electricity. In summer, most of the energy is made from solar panels, but we still need a bit of petrol power. In this particle container, there's a hydroponic farm. There's also all the recycling for the water. So 90% of the water is recycled, like in a space station. It actually brings to odd things while you're there. You can't, we had to use baby soap, and you can't bring your own soap and shampoo, and that's because of the water needing to be recycled. And the highlight of the base is this orange container in the back here, which is the sauna. So the excess heat from the power station is making a sauna, and then we can use it on Sunday. This is what it looks like inside. So this is the noisy tower. You see 3 levels, and there is a bridge in between on the lower level. You have a workshop here. You have all sorts of things. So there is a sorting and recycling facility here. You have here sort of emergency power. On top, you can see a lot of storage, cold and dry rooms, mostly for the wintering crew, and sports room and sort of cinema as well. And on the top floor, where most of the action happened, we had the dining hall, the living room, And here is where we clean the dishes, and everybody has to put their hands to it. So the chefs take care of the food, but then the cleaning of the living quarters and the dishes is done by the crew, and there's a rota, and everybody does it. And usually music is very loud and it's really fun. The quiet tower is this one. So you have the hospital, and there is a doctor there who has been trained in all sorts of situations. Typically, they've been trained actually like submarine doctors, so they can perform surgery, they can perform dentistry, they can perform all sorts of things, and they stay throughout the entire winter. And the doctor from this winter, she was the life of the station, let's say. She was a very, very good character. She was not just healing people, you know, physically, but also mentally. She was a very, very nice person. You have also like various other rooms here that are used, notably the firefighters' equipment and all sorts of things. The staircase are in the center every time. And then you arrive to the bedrooms. My bedroom was this one. It was the nicest bedroom. And that's because right next to me was the laundry, which was no noise. And I had a direct view on the telescope. So I was really, really pleased with that. The showers are here, and you see there's only something like 16 bedrooms, yeah, and only 13 people stay for the winter. For the summer, the base can accommodate up to 45 people, up to 50, I think. So most rooms we share, we have 2 people per room, and then they're lodging outside as well. And I stayed outside for a little while. And on the top floor, you have the control tower for the plane, for the radio, because we need to radio every time we go out, and labs for the glaciologists to study, you know, various isotopes in the ice. There is also people who work, you know, on the astronomical data, and the chief of station has an office up there. That's what the telescope looks like. So that's our dome. That's the telescope. Light comes from the top here. That's the mirror, the primary mirror. We have a secondary here. It's a Newton telescope. And this is the instrument bay with the 2 cameras. I'll show that to you in a minute. You can see space is quite small, but the telescope, you know, has a fair amount of room. You can see here the old pillar and the old telescope mount, and I'll show you in an instant the new mount and stuff. You see the base here, you see how we're located. We have a sort of lovely called Astro lab here, which is away from the station where we work. So we're close to the telescope and can run back and forth when things are there. When I was there, it was between -35 and -40. And oddly, you know, with the Apollo equipment, you really start feeling the cold from -50 down. At -30, it feels hot, and you really get used to it. So that's other pictures of Concordia. You see here we were in the departure hall in Christchurch. Here is the crane installing the new mount. You see it's different, and the new pillar, which is inclined to respect the axis of the Earth. And the finished product is here. So the telescope was installed. All of those paneling here is a lot of insulants, and between the insulant and the main part here are everything where you see a little bit of orange here. These are resistance to heat constantly the telescope, because the electronics cannot go below 50 degrees. Otherwise, things start snapping out. Actually, plastic at -40 is brittle like glass, so you can break things very, very easily. Even there's a weird logistics, because when you install things here, so this was stored in the Astro shelter in this workshop here, which was at 5 degrees above 0. But when we move it out, it's -40. So all of the screws might not always fit, and you have to really be quick. And, you know, time is important, because the temperature there's a temperature difference between the various parts of what you're handling, which makes matters a little complicated. And we had to install everything here. So this couldn't be above a certain weight, otherwise the crane couldn't really come to help us. And some bits, the insulant is fragile, but we had to install this and connect it to electricity in a certain time. Otherwise, things would start degrading, and then the telescope would be totally wrecked, and then we'd need to come back the following year. You know, it really edges on a few things. Antarctica is a bit cruel that way. You need everything in triple, because obviously you're going to lose your Allen key in the ice, and then, you know, the nearest one is 5,000 kilometers away. So fortunately, the workshop can make you things if you lose them, but yeah, it's a tough place. But eventually it all worked, you see. It's all beautiful, we're all happy. And here was the big unveiling of the telescope. One thing that really marked me while I was there is this. So when you're in Dome C, and I'm going to tell you what's odd is that there is really nothing out there, but actually the feeling of seeing nothing is really strange, because it's impossibly flat like the ocean, except nothing's moving. At least the ocean has wave. There is no smell, because there is no organic matter at all. There is no sound when you step away from the base, and there's absolutely nothing. And here, as an astronomer, it's sort of weird, because I really had that sort of, you know, it made the habitable zone very real. You suddenly were out of it, and it's not a good space. It's not meant to be lived. And it really crystallized in my thought that really what's interesting on Earth and why we enjoy everything so much is because of life. You know, every smell that we have, everything that we see that moves, everything is alive. And over there, everything is dead. And it's really the most desolate place I've ever set eyes on. And I've spent a lot of time in the Atacama. There's not much life in the Atacama, but there's a lot compared to there. And yeah, it's an odd feeling, but yeah, it changed my perspective. And all the people that described it, like I'm describing it to you, being there was, was something. So the trip back, this was my ride home, and it was lovely. I spent 10 days on board, 6 crossing the ice, crossing the sea. And I can't show you Antarctica without showing you these little people there. I was lucky to arrive in Dumont d'Urville just when the chicks were about to leave, and so they were approaching. They're a bit indecisive. They took 3 days to ponder at the ocean before they went. And obviously, they all went into the water during mealtime, so we didn't see them leave. This is the boat leaving Antarctica. So we go through the pack, and you can sort of see the vibrations of the camera is the boat crushing the ice underneath. And so that was for a few hours until we were in open sea. And that was also an interesting, I really liked being on the boat. And so it's a series of interesting experiences, but the boat also shows you the limitations of what you can build there because of the size of the back of the boat where you can put containers. There's only so much space reserved, and most of it is for oil because you need to keep people alive in Antarctica. So why are we going there? So after all of those nice pictures, you know, it's lovely. It's a lovely trip. But I think, well, you know, tourism in Antarctica, let's say, is a controversial topic. So let's not be tourists and let's be scientists. Why are we going there? So the astronomical advantages of Dome C is that we have a nearly continuous night from mid-May until the end of July. And that's really by far the main thing that is interesting. We have also very good weather, so we can observe nearly 80% of the time, like the best astronomical sites on Earth. And there's a very slow wind in Dome C at about 3 to 5 meters per second, which typically is the sort of slow laminar wind that creates the best seeing conditions in astronomical sites. There's a very low atmospheric pressure. It means that there is less atmospheres between us and the star, so things get less twinkly, and that's good for measurement. We have also a very low atmospheric water content. There's 10 times less water vapor in air column than in Chile. And so it means that observations that are affected by water vapor is good in Antarctica. Now, here it highlights a point that I think is kind of ironic in exoplanets. So we want to find liquid water on planets, and we want to find habitable planets, but we're forced to go to the most inhospitable, inhabitable places on Earth in order to detect it, because the very presence of water in our own atmosphere prevents us from detecting water in another planet's atmosphere. And so going to a place that doesn't have water is actually rather good. So at the moment, we're not doing atmospheric measurement from Antarctica, but if one day we do, it's because of this. And then something that we're not doing at the moment also is that we have a cold sky and it's cold outside. So the optics is cold. So it would be great for infrared astronomy. And I'll show you a project that is in development. And at the moment, we also know that at 30-meter altitude, the seeing, so how sharp your images can be, they are twice better than the best sites on Earth. And so for people who are astronomers, amateur astronomers or work with data, the average seeing at 30-meter altitude is 0.3 arc seconds. And at 17-meter altitude, which is just at the tower where the living quarters are, 50% of the time you get a seeing of 0.3 arc seconds. So it's really good for several reasons, because when we measure our data, like most people think of telescope as, we need a certain signal to noise ratio in order to measure something. And people, when they think of the telescope, they build bigger mirror in order to improve signal. But what we can do in Antarctica is that we don't care about the big mirror, we reduce noise. And so reduction of a factor 2 in seeing gives you 4 times less background in the infrared. And so very rapidly, you can make a very modest telescope to be the equivalent of a large one. And if my calculations are right, a 2-meter telescope in Antarctica would have the same signal to noise ratio in the infrared as an 8-meter class telescope. So it's a massive, massive improvement. And on an 8-meter class telescope, there's so much competition, you can't do stuff. Like, for instance, probably 5 or 6 Nature papers were published using the VLT, and each of them had less than 5 hours of telescope time of data in that. What if you had 2 weeks to observe? What could you detect? That's what Antarctica can give you. So with the current 40 centimeter, that's what we can do. So we detect long period planets. So TOI 791 is being published by one of my former students. Actually, she's the one that won the RAS prize. This is a 12-hour long transit. This light curve here is 24 hours. This is not what you can do from a regular observing site. You can see the transit in full. Here you see the sky background. So this is the twilight. So even in the middle of the austral winter, eventually the sun comes close to the horizon and you see a wee bit of twilight and you see it interrupts the light curve. But if you were in Chile, you had an 8-hour night, you might be only seeing the bottom of the transit and not even know you had a transit. Or maybe you'd observe here and then it would be day and then it would be night and you would have missed your transit. So having nearly uninterrupted data is really a boon. This year, so that's with a new mount, we captured a planet on a 508-day period. There's only 1 transit every year and a half. Imagine, and we have good conditions. We have a permanent night. Here, the whole light curve is 16 hours. So we didn't use the whole potential, but it's a very, very long night. And here you see both cameras. So we observe in the red and the blue. And you see the same signal in both cameras, which tells you that it's a planet. The radius is not changing. A binary star, for instance, would have a color difference between both events. And that way, for rare events like this, we can immediately validate them as they're planetary in one go. And just to give you an indication, at the bottom here, I put the insolation. You remember the temperate zone, from 4 times Earth to a quarter times Earth. You can see we are in the same sort of area here. So I tasked Georgina to tell us, to simulate, what we could observe. And so she simulated here planets between 20 and 200 days and all sorts of things, and compared it to other sites like in Australia, in South Africa, and in the Atacama Desert. And what's important to see here is the percentage, which is the color here, and the number of events that we can capture from Antarctica versus everywhere else. And you can see that most of the places is near 0 because the day-night cycle prevents you from detecting a full transit event. In fact, according to our number, only 6% of the events we can detect from Antarctica are actually detectable from elsewhere on Earth. 6%. So we have a 94% uniqueness ratio, effectively. Like we're the only ones able to make that measurement. And there's perhaps no better way to show it than to describe to you circumbinary planets. So that's my latest hobby, so to speak. So you have 2 stars that orbit one another and a planet orbiting both of them, like Tatooine in Star Wars. And now this is a fascinating type of system to study planet formation. It's extend the sort of realm of possibility of where planets form and all sorts of interesting aspects to it. But what interests us here is that you remember when you have a transit, you usually have a static star, single star, and then the planet transits, and then every X days, the planet will come back in transit, right? Here, your light source is moving. So your star is moving like this, and then your planet needs to catch that one. So when the transit happens, it's difficult. In addition, we know that the three-body problem is not solvable. We can only solve it numerically. And so while we don't know the planet's parameters very well, then predicting when the next event happens can be very difficult. Just to give you an idea, the orbital period of this planet is 95 days, plus or minus 5 days. And it's not because we don't know it, it's because the orbital period changes because of the two stars. So the orbit is always changing. And in addition, the two stars keep moving. So you need to figure out how to capture the transits. And no one has ever managed to get the transit of a circumbinary planet using a ground-based telescope. They were all done with space facilities because you can observe for 2 years at a time or something like that. So you can't miss it. But we've done it. And we've not done it just twice, we've done it 5 times. And we've done it by observing 48 hours at a time. And so we captured it, and now we can actually predict when the transits are happening. And so now we're applying for James Webb Space Telescope time because we know when this planet goes in front of the star, so we can study the atmosphere of that planet. And that's one of the reason of Antarctica is like small telescope allow you to access big telescope to do science that nobody else can do because nobody else knows where this planet or when this planet is going to transit. And we're going to be able to do it. The other thing that we can attempt doing are phase curves. So phase curves, I remind you, is the waning and waxing of the planet as it goes about. We see the day side, we see the night side. So this is the paper that made me go and enter ASTEP because they tried on this planet with 19b. They observed for 3 weeks continuously, and you sort of see a hint of that phase curve and the secondary eclipse. It's a hint, but this is a 40 centimeter observing in the optical. If you did the infrared, this would be obvious. In the orbital period of the planet here is something like 18 hours around the star. So 18 hours, it does this signal. And this is, so 3 weeks, you would have to divide 3 weeks by 18 hours and you'd see how many, times the signal has been effectively collected. But we could do it in only 2 or 3 days with an infrared telescope, and I'll show you that project. This measurement is widely considered impossible to do from ground-based telescopes, and only space facilities have again done it. But I believe we can do it from Antarctica, and that's the next thing that we're going to try to do. So brings me to the future, the cryoscope. And that was an idea from some partners at Caltech. Eventually, what they want to do is a 1 meter telescope, which is vacuum sealed, cryogenically cooled, operating in K-band, in K-dark. So it's in the middle of the K-band at 2.3 micron. The idea of that telescope is to do exoplanet discovery. We could do phase curves, brown roof weather, all sorts of things. The main thing that interests them is to do transients. So because of the unique conditions of Antarctica, with this 1 meter telescope, you could actually do as much, the discovery power of the telescope would be the same as the 8 meter Rubin telescope, which is about to come online in Chile at the cost of $1 billion of construction. Here, for 50 million, we might be able to do the same. So this sort of a telescope needs practice. And so there was a Pathfinder that was meant to be designed. Oh yeah, I forgot that. There's another good reason to go to Antarctica. You don't have Starlink. So we just have enough to get internet, but Starlinks, there's only 6,000 of them at the moment. They will grow to 40, 50,000 eventually. This is the plague of astronomy, notably for transients, so supernovae, for asteroid detection in the solar system. From Antarctica, there's nothing. There's no customers, so he's avoiding us. So it might be the only non-polluted sky. So normally, and I will show you a little bit the difficulty of Antarctica as well. So normally this year, we were about to roll out on the ice a 26 centimeter cryogenically cooled, vacuum sealed Pathfinder. So it's a smaller telescope with the idea was to see whether the sky was actually as dark as planned in that particular band. So it's also built by the partners in Caltech. So during 2024, Pathfinder was tested on Sky at Palomar. It worked. It was meant to be shipped. And then sadly, there was a problem with, I think, the vacuum. And normally it was meant to be shipped to Concordia and arrive there and be installed now on the ice. But because there's that problem, it sets us back a year. So it will happen in a year. But normally, this 26 centimeter should detect each single secondary eclipse here. So this signal here for each passage at 10 sigma, right? So uncertainty is 10 times smaller than the signal at each event. And here, remember that you had probably 3 weeks, 20, 30, there probably were 30 events here in order to create something that is barely distinguishable from the noise. And normally, we should detect that from a factor 10 from the noise in each passage of the planet behind the star with this small Pathfinder. This is just the prototype. Imagine what the 1 meter would eventually allow us to do. So that's pretty much the end of my talk. What I'll finish is to say that to better study exoplanets and to do all sorts of other astronomy, the Antarctic plateau is a really, really crucial site. And at Dome C, we can do astronomy no one else can. Before taking your question, I want to just thank my various collaborators, students, and postdocs who have helped make this happen. And I'll take your questions now, and I realize I went a little over time. I don't bite.
Quick question, if I may.
Yeah.
In the last slide, the one where you see it was to detect the signal to noise.
Yeah.
The one before, the one where we see the signal to, yeah, that one. Do you use a statistical model?
What do you mean?
Is there a modeling to see this change point going up and down? How do you do this red line that we see?
This red line, oh yeah. So the transit is a semi-analytical model. This is then on top you have a sine curve. And this is another semi-analytical model. And this is usually compared using Markov chain Monte Carlo sampler or something like that, using, you know, highest likelihood type thing. I don't know what field you're in, but yes, it's fitted statistically.
And how did you prove that?
I'm not sure exactly which one you refer to, like you're like the computation of the red line or how the red line gets adjusted to the data.
Gets adjusted to the data.
This one was a Markov chain Monte Carlo. MCMC. Yeah. Yeah, so the MCMC typically will generate millions of models, compares them in likelihood, and then it chooses the highest likelihood over another, and sometimes the slightly worse likelihood with a certain probability, which allows to explore parameter space and give you very good, robust uncertainties.
Zoom does not have any questions for us, so if there are any other questions, feel free.
In one of your first slides,
Yes.
you had 3 clusters of points, and you commented on that.
This one?
Yeah, that one.
Yeah.
What do we see? Is it technical? Is it showing? So this cluster comes from our ability to see, or come from the reality of the planet behind them? Hope it makes sense.
Yeah, you do make sense. So the lack of planet in this triangle, it's our ability to see. So what we need to realize is that to find Jupiter, that's an 11-year period. You need 2 periods of the planet to confirm it. So that's 22 years of work. Exoplanets have been detected 30 years ago, so we're here. These are probably projections or people who started early, or sometimes another method of discovery called direct detections. Some of those might be another method called microlensing, where they see a slight effect caused by general relativity when there's a planet near a star, but it's a rarer type of method. So the fact that there is almost no detections here doesn't mean that there is nothing. It's just our ability to see. And typically here, there's a sort of threshold, or while the best instruments are here, but then they need to operate for several years before the precision that is here extends all the way there. So only the early instruments were sensitive, or now sensitive to that period, to those orbital periods, but then they have a worse precision. So what is the patterns that are clear is that a deficit of planet between these two, that's for real. The relative height of the number of planets here to here, that's not, because these are a lot more easy to detect. I mean, this is 1% of a year, so that's 3-day orbit. That's, you know, in 2 weeks of work, you can find, you know, a few planets there. But here, that's several years of work, so it's going to affect you. The lack of planet in this triangle, that's also real. And the weather, there is this, you know, like it looks like there's a sort of peak, a trough, and another peak in this direction that is being investigated. It's not totally clear whether that area is relatively unpopulated or not. The relative probabilities, so this is 1 sun-like star in 200 will have a hot Jupiter. 1 in 10 will have a gas giant in this sort of general area. And 1 in 2 will have a planet around here. So if you count all of them together, it means that already you've sort of counted about 60% of stars. So it means that solar system-like are at most, you know, 40% of stars, effectively. So they can't be really representative. That's the main picture we take from that. Now, the main thing that people think is that planets form around here, they grow in mass, and then they start migrating. And some of the migration stops here. And so these objects are understood from migration. That's an exchange of angular momentum between the disk and the planet. And then interactions between the planets. So if you have 2 planets in the same system in this area, we'll send maybe the inner planet on a very eccentric orbit, and then it will circularize here due to tides. So this is a bit of a special population. That population is unclear. It could have formed further out, or it could have formed locally. That's the big question. People don't know. My bet is on it did both, you know, but because nature is in such a way. But we have to investigate that. We expect that the chemistry of the atmosphere will be different. So if you're formed further out, you will have a lot more volatile, like water and stuff like that, whereas you'll be drier if you form locally. And so we should see that when we measure the atmospheres.
There are many other things. We are.
There's one.
Oh, sorry.
Yeah, just a quick question. Can aurora be a problem for observations in
It's a good question. So we thought at first, yes, but actually for what we do, no. And the reason is because the aurora is usually in very narrow bands, so we don't really see it. Even, you know, if I don't know if you've seen the Northern Lights when they happened, you know, like in the past year, you still see the stars usually fairly well. And our cameras work the same way. So if the auroral display is particularly bright, it can become a bit of a nuisance, but not too much. The thing too is that from Antarctica, so we are here, and the magnetic pole is here. And so the auroral ring is here. So it sort of avoids us. So we're not the most, you know, sensitive to it, let's say. This summer when I came, or last austral summer, I saw the Southern Lights on boat. So it was weird because we left here, and for 2 months I'd been living by permanent daylight. And at some point I woke up, we were here with a boat, and it was night. And I was like, oh, how am I going to go to the bathroom now? And I said, okay, 2 seconds to realize, yeah, I know how to figure night out. But then the following evening, I thought, oh, let's look, maybe we'll see the southern lights. And indeed, we saw them. They were just there from the boat, but we had to be away from Antarctica, weirdly enough, to find them. So by and large, not a big problem for us for the exoplanets stuff. Also because we work by targeting one objects and comparing the lights of many others in the field. And so we're not as sensitive to that. If you were to do faint object astronomy, trying to find, say, the motion of an asteroid within the field of view, or trying to find a supernova, then it might affect you because your background would be more elevated.
On Jupiter, do we know if they form near the star or do they move in from far?
Yeah, so the main, it's widely thought that they have to move, they have to form far. Like there isn't enough material to build a planet there. But we've been wrong in the past before. Exoplanet formation model predicted there should be absolutely no planet in this area, and 50% of stars have one. That said, the models that show that the planets can't form locally there seem to based on fairly, good simple physics, and it's a lot easier to explain why, a handful of these would have a special story, 1 in 200, it's very, very low probability to be a hot Jupiter, than to create an entire pathway to create this and explain why there is nothing in between.
Like Earth move away to the distant side.
You mean escape the system?
No, move towards where the cold Jupiters are, like a planet of Earth size. Like if a hot Jupiter can move.
Yeah. So actually, yeah, so this migration can go both ways. Planet can move in and can move outwards. It depends on how the angular momentum torques go into the disk. By and large, most things go inwards, but there are times where the planets can go outwards. It is actually thought that while in the solar system, one of the hypotheses is that Jupiter migrated almost to the orbit of Mars, and then got caught by Saturn. Saturn has a lower mass than Jupiter on the outer orbit, and it inverted how the angular momentum, the response of the angular momentum between the disk and the planets. And then the pair moved outwards. At least that's one of the models, one of the explanations. And it fits some of the observed data that we see in the solar system, notably in the population of asteroids in the belt and things like this very well. So whether this happened or not is another question, but it's a good explanation for what we see. Yeah. So yeah, it's a good question. There's a mix of various things that we do. So we have a program that favor long transits first, because we're the only ones that can do them. So we thought, well, let's do them with a priority because we have a unique discovery space. We also favor typically long period for several reasons. Again, because it's very hard to capture, but also because I have an interest in that. At the moment, we don't know of any moons outside of the solar system. Like there are 300 moons in the solar system, and we have found 0 moon on exoplanets. And the main reason why there are no moons is probably because of the migration that we were talking about with planets. And if you look at the solar system, the nearest moon to the sun is our moon, right? 1 year period. So you need long period planets. And so I'm hopeful that we will build a catalog of these long period planets where we accurately know the period and can look for moons. That'd be fun, right? That's one fun topic. Again, like that's the answering the, well, we go back to the original science questions, answers the middle question first, just it's cool. So, people will be interested in that. And then trying to understand the physics of planet formation, because understanding the moon formation and how they remain would be interesting. Then, you know, circumbinary planets are just a topic in itself. So Antarctica is the only one, so that's a fairly obvious choice. We also do a set of targets I haven't talked about. So if you have two planets that are in an integer ratio of periods, so for instance, if one planet orbits in 10 days and the next one in 20, you have a 2-to-1, or you know, something like that. And when this integer ratio of orbital period happen, typically the planets are exchanging a lot of angular momentum and orbital energy. And so it means that the planets come, the transits come early and late, and it allows us to measure the mass of the planet. And these are very difficult to measure because typically we need to collect something of order 30, 50 transits across the two different frequencies of the planet. So every time there's a conjunction, there will be a kick, but then those kicks move apart from one another and then come back. And so there's two periods to sample. And sometimes it can take 10 years, 30 years for the outer frequency to be fully resolved. And with ASTEP, we have a huge chance because most of the planets that do this sort of dance, they have long periods. So if you have a 10-day planet, typically it will transit once from Chile per year. And that's not because, and yet the planet transits every 10 days, but you can only capture one transit from a night from Chile. And that's because otherwise it'll be in the middle of the day or partly half in a day, half in a night. There'll be clouds, there'll be the moon, all sorts of things. So, whereas for us, like this year, we had somebody ask us, "Hi, we just discovered this new planetary system, and the two planets seem to be doing this sort of dance. Could you get us one transit on both planets?" We said, "Would you like 15?" You know, and that shows, you know, what we can do that others can't do effectively. Yeah, so that's the other choice. So those are scientifically motivated, but then not all of the time of the telescope is used. And so then we fill in the blanks, being opportunistic. So there are thousands of candidates out there, and there will always be one pretty much transiting at any time. And so then we go through the list and take, you know, what takes our fancy, what's detectable, whether we can get the full event or not, because it's better to get a full event than a partial. And yeah. Yes.
You said that we could see moons. How do you think what's the method in which they would be discovered? Will we see a difference in the star's light?
That's in principle, yes. So if you have a planet and that planet has a moon next to it, either the moon will pass in front of the star first or it will pass after the planet, right? So you could see a small dimming here first, you know, like what we were saying actually on this plot. Remember that plot? There are 3 planets, right, in there. But it could equally have been, you know, like this is a moon of the other one, you know, and then you see this sort of weird signal. The problem is that most moons are small. If you take the biggest moon in the solar system, Ganymede, is bigger than Mercury, right? It's a very big moon. Well, at the moment we have a trouble finding Earth-like planets. You know, we're working real hard to take that. Finding something which is 1/10 of the size is at the moment not possible. So directly detecting the moon seems unfeasible unless the star is very small, or unless we observed, we knew at the right time and used like a really performant telescope like the James Webb. But to search for it, you can't use the best telescope to search for it because you're going to waste a lot of telescope time on things that don't have moons. But it turns out that if you have orbiting objects, you have a planet and a moon, what happens is that, you know, the central object will move a little bit, right? Because it will both orbit around a common center of mass. And so it means that sometimes the transit will be a bit early and sometimes it'll be a bit late because of that unseen companion. And that's those variation in arrival time of transits. We call them TTV, transit time variation. So the same thing that happens when you have 2 planets that talk to one another. Sometimes the transit is early, sometimes it's late. If there was a moon, it would be sometimes early, sometimes late. And it will be as early and late as the time it takes from the planet to be on one side of the center of mass to the other side. And so we can predict that. So yeah, we'll be on the lookout. Although this will take a while. If there's a moon around that, we can only collect one event every 500 days, but every 500 days, so this was in the austral winter, Next transit in a year and a half will be in the austral summer. It'll be daylight, so we'll miss it. So we'll have to wait 3 years until the next one, and that's 2 events. And we need to wait 3 more years. You know, so I don't know. That's 1 PhD, 2 PhD, and we have 3 events. So it will take a while. We'll accumulate data. Hopefully, we'll find a shorter period planet to do that on. But yeah, we'll have to accumulate data over decades to start seeing those signals.